This is day 48 of 50 days of tutelage, and in today's class, I'll be talking about alkanes and alkenes. In previous class, I taught you about organic chemistry and the general introduction to what carbon is like and the fact that they have the ability to form different types of compounds based on catenation, based on formation of variable bonds and all of those things. So starting from those bonds and the like, I explained that you can have a carbon to carbon single bond, you can have a carbon to carbon double bond, and you can have a carbon to carbon triple bond. So we're going to be starting from this particular place today. For alkanes, they are those hydrocarbons that they only possess this carbon to carbon single bond. You cannot find anything like double bond or triple bond in them. And such hydrocarbons are actually called saturated hydrocarbons. That is, such hydrocarbons that every single every carbon to carbon bond there only exists as single bonds, single covalent bond. You cannot have any double bond there. So hydrocarbons that are saturated hydrocarbons, that is, all carbon to carbon bonds, they are single bonds. They are called the alkanes. And they have a general formula. The general formula is simply CN H2N plus 2. So where N varies from 1, 2, 3, and it goes on and on like that. So for instance, if the first member of the group is going to be C1, then you have H2 multiplied by 1 plus 2. So when you do all of these, you have C. So we don't need to put the 1 because just 1 is a subscript there. So 2 times 1 is 2, 2 plus 2 is 4. So we have CH4. This first guy is actually known as methane. So if you continue like that, and if you remember the last class, I told you that there's something called homologous series. So these alkanes also have their homologous series. I told you that they always increase by 1 carbon and 2 hydrogen atoms. 1 carbon atom and 2 hydrogen atoms. So if you apply this formula now for C2, that will be C2H2 times 2 plus 2. If you do this very well now, so you have C2. 2 times 2 is 4. 4 plus 2 is 6. So you have C2H6. So if you look at this now, it has increased by 1 carbon and it has increased by 2 hydrogen atoms. And this is ethane. This is ethane. So this is what generally the definition of alkanes. This is what they are. Of course, we have other ones as well. We have propane, we have butane, we have pentane and hexane and all of those things. So as we continue to go in the class, I will be introducing them to you one after the other. So we have different members of this class. Another thing you should know about them is that for the first members, that is the ones that have like 1 to 4 carbon atoms, those members that have 1 to 4 carbon atoms, they exist as gases. And for those that have from 5 carbon atom to 12 carbon atom, those ones exist as liquids. They exist as liquids, and anyone above them exists as waxy solids. So they vary like that. I explained in the last class that in the homologous series, one thing to notice about them is that they have similar chemical properties, but their physical properties tend to vary as you go down the group. So we can see the way they exist and then the state of matter and all of that as well. Another thing you also notice is that they are non-polar. Because what we have here is carbon to carbon bond, and then another one that we have there is hydrogen bond. Of course, most of these carbons are bonded to hydrogen. And then between carbon and hydrogen, what we have there is actually a covalent bond, and it's not a polar covalent bond. If you're going to have your polar covalent bond, you know the what hydrogen has to bond with. That's when we have hydrogen bond and all of those things. So, but anyways, I'm not going to be talking about those ones now. I've discussed bonding in a previous class, polar, covalent bond, and the likes. So you can check the playlist out for chemical bonding. So back to this one now. So they are non-polar. So that means that they are not going to be soluble in water. They're not soluble in water, but they are soluble in organic solvents. And for boiling point, is a physical property. Boiling point increases as the molecular mass increases. So as you go down the homologous series, their boiling point also increases as well. Due to increase in what? Increase in molecular mass. That causes stronger van der Waals forces to be generated, because the higher the molecular mass is, then the higher the van der Waals forces as well. So that's that about that. Alkanes, they do not really undergo many reactions like that, because like I said, they are saturated. So there's a kind of stability in them. They don't really undergo chemical reaction like that. But one of the chemical reactions that they undergo is combustion. So combustion, they can undergo combustion. And you have this general formula for their combustion. So if you have Cn, H2n plus 2 reacts with oxygen, that is combustion, it will give us CO2 plus H2O. So generally, to balance this equation, all you have to do is, whatever the n is, just do this. You have 3n plus 1 over 2. Then for the CO2 part, you have n there. And then for the H2O part, you have n plus 1. So what I'm trying to say is that, for instance, let's pick just a random one. Let's pick butane now. Butane will be C4H10. 2 times 4 is 8. 8 plus 2 is 10. So C4 plus O2, that will give CO2 plus H2O. So to balance this now, so we have 4 carbon atoms here. We have how many carbon atoms? Just 1. So let's say we balance this with 4. We have how many hydrogen atoms do we have here? We have 10 here. We have this here. We have 2 here. So to balance it, that will be 5. 5 times 2 is 10. And then we have oxygen atom. We have 4 times 2. We have 8. 8 plus 5, that's 13. So 13 will not really work. So you can say 13 over 2 in this place. You can balance it out by multiplying everything through by 2. You can multiply everything through by 2. So you have 2 C4H10 plus 13O2, then 8 CO2 plus 10 H2O. Since if you don't want fraction to be here. So, but if you apply this formula directly, it will just give you the whole result. So 3 times 4 is 12. 12 plus 1 is 13. So you can put 4 here, and you can put 4 plus 1, 5 here. So this formula will help you to balance the equation so fast. But you can also balance it normally. I've also taught how to balance chemical equations as well. So that's the first reaction that they undergo. Like I said, they don't really undergo plenty reactions like that. So they undergo combustion. The next one that they undergo is substitution reaction. They undergo substitution reaction. What is substitution reaction? So for alkanes, if you have alkanes like this, let me 1, 2, 3, let me make it 5. You have hydrogen here, 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 you have hydrogen. By the way, this structure is called the Kekulé structure. Yeah, it's called the Kekulé structure. Very soon I'm going to teach you about the zigzag structure. And that one is going to be very, very helpful in analyzing some other things that I will talk about later. So in this place now, this is pentane. We have 1, 2, 3, 4, 5. 5 carbons. How many hydrogen? 1, 2, 3. Of course, 5, 5. That would be 10 and 12. So we have C5H12. Now, this guy can undergo substitution reaction. What do you mean by substitution reaction? Is basically if you react it with any of these halogens, whether your fluorine, whether your chlorine, whether your bromine or your iodine. So if it reacts with any of these things, they can be substituted. So whereby one of the hydrogen will be replaced by the halogen that you are using to replace it. So in that case, they become what? They become haloalkanes. In that case, they become haloalkanes. And for haloalkanes, there's something we call alkyl group actually. Alkyl groups, yes, alkyl groups. Alkyl groups, basically all you need to do is to just sacrifice one hydrogen out. When you sacrifice one hydrogen out of an alkane, you get what we call an alkyl group. An alkyl group, they always play a very, very important role in different reactions because they always constitute a part of the compound that you are forming after reaction has taken place. So if we try to jettison this last hydrogen now and replace it with something else, let's say a sort of an halogen, so we have X here. So in this place, the alkyl group is actually this. So we have pentane. So the alkyl group is going to be pentyl. It's going to be pentyl. And then when you bond that with this, so we represent the alkyl group with a R. So R represents alkyl group. So R will bond with X. This guy is an haloalkane. Haloalkane. So this X is what gives the halo because it's one of the halogens. So during substitution reaction, one hydrogen or two hydrogen or three hydrogen might be replaced depending on how well you are reacting. Maybe you are reacting any of the halogens in excess, so they become alkanes. I'll come back to naming later. And let me just deal with this reaction of these alkanes first. So that's basically the major thing that you need to know about alkanes. Now, let me talk about the structure now. So I was talking about this structure earlier. This is called the Keku structure. So we want to see how we can actually name them, and we want to see another type of way we can also draw the structuring. This new way that I want to draw the structuring is going to actually help us understand the concept of isomerism. So before that, let me teach you about naming first. How do you name an alkane? To name an alkane, basically what you do is that you count the longest carbon to carbon chain. So if you have, let's say, something of this nature now, you have this, 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 you have this. Permit me, I may not be able to write all the hydrogen, please. You have this. This one also has its own hydrogen. There's hydrogen here. There's hydrogen here. You have hydrogen. There's hydrogen here. There's hydrogen here. So one thing we noticed about carbon is that there must always be 4 bonds around the carbon. I have explained that in the previous class. 4 covalent bonds around the carbon. So that is why for every empty whatever, there will always be hydrogen filling it up. Now, so let's look at this guy now. The longest carbon to carbon chain that we can count here is going to be, so I can count different branches. I can count from here 1, 2, 3, 4, 5. That one is gone. And I have 1, 2, 3, 4, 5. Another 5. There's 1, 2, 3 as well. There's 1, 2, 3, 4, 5. That's another 5. There's 1, 2, 3, 4, 5, 6, 7. Now, when I say carbon to carbon chain, you must be able to count them continuously. Not as if you jump from one and you move to the other. Like this, you must be able to place a straight chain that connects all of them together like this. So we have 1, 2, 3, 4, 5, 6, 7. So we have the longest carbon chain here is 7. 1, 2, 3, 4, 5, 6, 7. So we pick 7 over the remaining 5 that we have counted. Now, we'll now look at each of these guys. So the parent name is going to be, since it is 7, 7 is hept. So is heptane. Now we now look at attachment here. Anything any carbon that is not part of the chain is going to be an attachment. For instance, this guy is going to be an attachment. Of course, this carbon is part of the chain. Let me engulf them. Yeah. So this carbon is not part of the chain. This is also not part of the chain. So when they are not part of the chain, they are regarded to as alkyl group. Don't forget. So if this one, if it was an alkane, it would have been CH4, the first member, methane. But now it is CH3, so this is a methyl group. This is also another methyl group. So now you want to name it now. These two will be regarded to as attachment. Then you count these 1, 2, 3, 4. So you can see that this guy has a carbon, this attachment, methyl group on carbon number 4. It's on number 4, it's on number 4. 5, 6, 7. Then you count again backward. 1, 2, 3, 4. Now, had it been that if as I was counting now, if the attachment had ended up on carbon number 3, I will always choose the counting side with the lowest number. I will always choose the side that I counted with the lowest number. That is, if you're counting like this, you have attachment here on carbon number 4. And if I count like this, you have attachment here on carbon number 3. You will go for carbon number 3 instead. That will be your preferred counting method. So in this place, this is carbon number 4. But we have 2 of them. So you say 4, 4. So 4, 4. Then you have dimethyl heptane. So you can see for numbers, I separated them with commas. But whenever I want to transition from number to letter, I separated it with an hyphen. So take note of that, a dash. So 4,4 dimethyl pentane and dimethyl heptane. Rather, this implies that I have 2 methyl groups and they are on carbon number 4. So dimethyl and all of those things like that. Anyways, this is just basic naming. There's a better video that I've made for naming as well. You can just check the pop-up. You see the better video that I've created for naming. I named different organic compounds there, and I gave some certain rules as well. So just make sure you subscribe to the channel as well. You get to see subsequent videos where I've actually like explained different concepts about naming different organic compounds and all of those. So this is just about alkanes and alkenes. So I will not spend so much time on naming here. By the way, let's now move to away from the Keku structure. So we have the zigzag method. Now basically we just represent compounds with lines, something of this nature. We have something like this, something like this, we have something like this. So this is the basic rule. Just know that at any endpoint, if you have any endpoint, what you have there is a carbon. And at any junction, what you have there is a carbon. So endpoints and junctions, they always comprise of a carbon. Once it is an endpoint, it always comprises of a carbon. So in this case now, we have how many carbons here? 1, 2, 3, 4, 5. With this structure is actually your pentane. Yes, this structure is your pentane. So the pentane that I labeled earlier, this guy, is the same thing here. So what if you now have something of this nature? You have this, you have this, you have this, you have this, and then let's say you have something here. How many carbons do we have here? So let's see. For the ends, let's count the number of ends that we have here. 1, 2, 3. 3 ends, that's 3 carbon already. Let's see the junctions. 1, 2, 3. 3 ends, 3 junctions. So what we have here is also 3 carbon at the junction. So we have 6 carbons altogether. Does that mean this is hexane? No. It doesn't mean this is hexane, because as you can see now, this is a branched hydrocarbon. This is a branched hydrocarbon. So for branched hydrocarbon, we don't just name them directly. Just like the way I not just call this one heptane, or because it has 9, I should now call it nonane. No, it doesn't work that way. So, which leads me to the concept of what we call isomerism. Isomerism. So, what is isomerism? Isomerism is basically when you have compounds that have the same formula. They have the same formula, but their structures are different. So we call them structural isomers. Structural isomers. For instance, the moment you begin to have any carbon, any alkane that has 4 carbon atoms and more, then you can begin to have isomers. For instance, let's start with butane. So butane, as you know it, is going to be C, 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 C. Then you have H, 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 you have H. Now, the best way to draw this, I will always use the zigzag structure. So you have 4 carbon atoms. So you have 1, 2 already, then you have 3, then you have 4. So with this now, what you have here is 1, 2, 3, 4. This guy is also this guy. They are the same thing. So how can we determine the isomers? Basically, what you begin to do is that you begin to break them down one after the other. So when I mean that by breaking them down, you remove one of these. So you go to one end, you remove one of the ends. So you can remove from the left end, you can remove from the right end. So I'm going to remove from here. So when I remove this particular guy now, I want to attach it to this place. So if I attach it to this place, I think I need to rotate that. Yes. I want to attach it to this place. By the way, that's the only option I have to attach this guy actually. I cannot attach it anywhere else. So if I attach it to this place, then I have produced a different structure. And let's see what this guy will look like. This guy will look like this. We have C, we have C, then we have another C there. But from this C, like I told you, once you have an end, it's always a C. So we have C here. So this structure is like this. So let's put the hydrogens around the carbons. So we have these, we have these, we have these, we have these, we have this, we have this. So let's count. How many carbons do we have here? 4 carbons. And how many hydrogen? 10. So we have C4H10. For this one, how many carbons? 1, 2, 3, 4. So we have C4H10 as well. Now, we have this. Let's now count the number of hydrogen. We have 3 here. We have 3 here. We have 3 here. That's 9. Plus this one, that's 10. So this is also C4H10. But the structures are different. In fact, the name is different. So this one is butane. But let's see what the name of this guy is. I told you count the longest carbon to carbon chain. There is 1, 2, 3. There is 1, 2, 3. There is 1, 2, 3. And which other one again? Yeah. So 3 carbon to carbon chain. So you can pick any one of them. So 1, 2, 3. You can see that there's an attachment on carbon number 2. And so because there's an attachment on carbon number 2, so we name it as what? And that is methyl group. So that will be what? 2-methyl. What's the longest carbon to carbon chain? We counted 3. That is prop. So 2-methyl propane. So 2-methyl propane is an isomer of butane. 2-methyl propane is an isomer of butane. And that is basically what isomerism is about. You can try for, see this is butane, you can try for pentane. You can try for pentane, you can try for hexane, and see how many isomers that you can get. Just follow this principle. Of course, this video will not permit me to be able to do as many as I would like to do. So let's proceed. Now, briefly, I forgot to talk about this type of carbons. We have what we call the primary carbons, we have what we call the secondary carbons, we have the tertiary carbons, and we have the quaternary carbons. Now, they are determined by the number of carbons that they are attached to. So for instance, if you look at this structure, oh my god, that was so wrong. So you have hydrogen, you have hydrogen, you have hydrogen. Oh my god, I hate writing all these hydrogens. So you have another structure here. You have CC, you have C, you have C, you have hydrogen, you have hydrogen, you have hydrogen, you have hydrogen here, hydrogen. I think please permit me to just be using the dash to represent the hydrogen. Then look at this other guy. We have C, we have hydrogen, we have hydrogen here. I have C, then I have C, then I have hydrogen, 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 hydrogen. Then what else do I have? Then I have another one here, C, 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 C. Then I have hydrogen, 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 hydrogen. Yeah, and all of that. So look at these 4 structures that I've drawn. So what are primary carbons? Primary carbons are attached to only one carbon atom. So you can see these 2 now, they are primary carbons. Because if you look at this carbon, how many carbons is it attached to? 1. How many carbon is this one attached to? 1. Now, if you look at this one, how many carbon is it attached to? Directly attached to, please take note, 1 carbon as well. So it's primary carbon. But if you look at this particular guy now, how many carbon is it attached to? Directly, number 1, number 2, and number 3 is attached to 3 carbons. So we have what? A tertiary carbon here. This guy is a tertiary carbon. And if you look at this one, look at this carbon now. How many carbon is attached to? 1, 2. So this is a secondary what? Secondary carbon. And then we have this guy. This is the quaternary one. It's attached to 1, 2, 3, 4. It is directly attached to those carbons. And this will actually also help you when you are naming tertiary and primary, secondary, and tertiary alcohols. It will help you to identify them. Primary alcohols, their OH group is always attached to the primary carbon. The same thing for secondary alcohol. Their OH group is attached to secondary carbon and all of those things like that. Anyways, I've dwelled too much on alkanes, and I think I need to move forward now to alkenes. So for alkenes, we start talking about the unsaturated hydrocarbon. The unsaturated hydrocarbon. And this one, there is the presence of carbon to carbon double bond. So you have a covalent bond, 1 sigma bond, and 1 pi bond. So one of these is a sigma bond, and one of them is a pi bond. So you have a sigma bond and you have a pi bond there. So I've talked about the hybridization in all these ones earlier. This guy is an unsaturated hydrocarbon, like I've explained earlier. And in fact, That unsaturation helps it to be able to be very, very reactive. And one of the tests of test for the presence of double bond is that they decolorize bromine water. Alkenes, they decolorize what? Bromine water. Bromine water, which has like a kind of brownish color or orange color, they become what? They become colorless when you react them with alkane. So that's the major test for alkanes actually. They also decolorize acidified KMNO4. They decolorize acidified KMNO4 as well. From purple, they become colorless. From purple, they become colorless. So we have different ways we prepare them. Alkanes can be prepared by the deterioration of alcohols. I don't want to talk too much about alcohols because alcohols, you have something like ROH. So when we say dehydration, I think I need to just talk about this. So let's say ROH. This is an alcohol now. So let's pick propane. So I'm going to be propyl now. So that will be HCCC. Then you have OH here. Then you have this, 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 you have this. So this is actually propanol. Now, if this is propanol, I can prepare alkene from this place. All I need to do is what? Is to just dehydrate. That is, remove water from this. And to remove water, I just need OH and I need one H. So therefore, this guy becomes H, CH, then there is still H there, there is CH, there is still H there. But this C now, there's no hydrogen here, there's no OH here. Only one hydrogen is left here. So we have this. But the problem we have here is that carbon, there has to be 4 bonds that surrounds it. There has to be 4 bonds that surround it. So because 4 bonds has to surround it, then there is a need for a double bond like that. So the need for that double bond, we have something of this nature. We have double bond here. But when you look at this, how many bonds do we still have around this carbon? Only 3 bonds. But when you look at this carbon now, how many bonds do we have here? 1, 2, 3, 4, 5. There are 5 guys here. So therefore, we have something of this nature. This guy is going to be here. This guy is going to be here. So dehydration of alcohols gives us what? Gives us alkenes. Gives us alkenes. So alkenes are generally represented with the presence of a double bond. They are generally represented with the presence of a double bond. Okay, so let's proceed. Now, you can actually check out other type of preparation. Their general formula, sorry, I forgot to say that. The general formula is CnH2n. By the way, they do not have the first group, methane. So their N always starts from 2 and above. So you have ethene, you have propane, you have butane, and all of those guys like that. I think I've explained basically most of the preliminary things about alkenes. And then how do you name them as well? Instead of having, I think I've explained already, instead of having butane, you then have butene. So from ane, then you change them to what? Ane. The only major thing here is that for alkenes, to name alkenes, when you want to count your carbon to carbon longest chain, you don't just count recklessly. You count such that all the double bonds that are present, you will always include them in your counting. All the double bonds that are present, you always include them in your counting. If I start naming now, so let me just choose a random thing to name. So let's say we have C, C, C. There's a double bond here. Then we have a C here. So let's say we have a C here. Then we have H here, H here. We have let's say we have okay. I'm trying to actually tailor this in such a way that okay, I want it to be terminal. So we have a C here. So we have H here. We have 1, 2, 3. So there will be another H here. So we have a C, another C in this place. So let this be H, let this be H, let this be H, let this be H. So how do I name this guy? Please forget about all the H here. There will be H, there will be H, there will be H in this place. How do we name this guy? So if you look at this now, you notice that 1, 2, 3, 4, 5. That means that I don't need any H here. Aha. So everything is correct now. So if you look at this now, the longest carbon chain will actually be 1, 2, 3, 4, 5, 6. Yes, it will be 6, 6. Contrary to if you count if you want to include this now, you have 1, 2, 3, 4, 5, or you have 1, 2, 3, 4. So the longest carbon to carbon chain now we are going to have is 5 actually. 1, 2, 3, 4, 5. We also have 1, 2, 3, 4. So 4 is less than 5. But we have 1, 2, 3, 4, 5, 6. Now, why can't I use the 6? It's because the 6 does not include the double bond. And by the way, how can you tell the carbon that owns the double bond? The carbon, when you are counting in your chain, the carbon must come before the double bond. So if I say 1, 2, 3, 4, 5, 6. So you might think 6 is correct because yes, this carbon has this, but the double bond does not continue my chain. So the double bond has to continue my chain. Like in this case, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes, the carbon 1, 2, 3, 4. 1, 2, 3, 4. You can see that the double bond continues my chain. So you prioritize the shortest path. So let's name this guy now. So I have my longest carbon to carbon chain will be 5 in this situation. I will not pick 6 because 6 does not include the double bond. So if it is 5, so I have Pentene. The best thing for me to do is to count here. That is 1, 2, 3, 4, 5. So with this, I have my double bond on carbon number 1. What will happen is that this other guy will be an attachment. And what attachment is that? Is 1, 2. That's like from the 8th group. So since now an alkyl group, it will be ethyl. So let's name this now. So that is on carbon number 2. So you have 2 ethyl pentene. 2 ethyl pentene. And that is the name of this guy. So you always have to prioritize the double bond in that case. And that's basically how you name your alkenes. You just have to practice more. And like I said, subscribe to this channel to always have access to any of my videos in the future, which I will actually be naming some different organic compounds and all of that. So for alkenes, they are very, very reactive. They undergo combustion reaction as well. So they also give, when they undergo combustion reaction, they also give CO2 and H2O. And then they also undergo what we call addition reaction. They undergo addition reaction. So what do you mean by addition reaction in this case? Addition reaction is simply, so if you have a typical alkene, so let's say you have your C double bond, then you have H here, then you have H in this place, then you have H in this place. So this is your ethene. If you have your typical alkene, what you notice is that it's like something is missing here. If it's going to become an alkene, you have 2 hydrogen missing here. So one of the things you can do is that you can hydrogenate like this. You add hydrogen. So hydrogenation. When you do hydrogenation, it just converts from ethene. It becomes ethane. So that's very simple. That is an addition reaction. So this entire thing is breaking the double bond and turning it to single bond. So each of the hydrogen will come here. They will come here and they feature there. Another thing we also have is hydrohalogenation. We also have halogenation anyways. Halogenation is also like hydrogenation, but this time around, instead of hydrogen gas, you probably have, let's say, bromine gas. So bromine will just come here and replace this, and it will become alloalkane. But we also have what we call allohydrogenation. Allohydrogenation. In this case, what we're doing is that we're bringing an hydrogen halide to react with this guy. And so therefore, we'll now have hydrogen come to one side there and the halogen will come to one side. So you also have alloalkane. However, this one is symmetrical. What if I have the case of HCC, then I have a double bond there, I have C here, I have H here, I have H here, 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 here. So in this case, if I want to react this guy with hydrogen halide, you notice that if this substitution should take place, that is, if I should delete this guy, if I should delete this bond here, and I place hydrogen here, and I place the halogen here. If I should name this guy, there will be a different thing. This guy will be on carbon number 1. But another way that this can also happen is that I can decide to place the halogen here and place the hydrogen here. The name will be different. So how do we determine which one, where will the hydrogen go, where will the halogen go? We use what we call the Markovnikov's rule. The Markovnikov's rule. And what does it say? For unsymmetrical alkenes like this, if you want to do hydrohalogenation, the hydrogen we add to the side with carbon that has more hydrogen there. So for this now, I want to choose where will my hydrogen go and where will the halogen go. So if you look at this carbon now, how many hydrogens do you have here? You have 1, 2. How many hydrogens do you have here? 1. So therefore, hydrogen will go to this place. Markovnikov will say that hydrogen goes to the side with more hydrogen, then the halogen will go to this place. So you have X in this place. So this is the way you do the addition reactions that involve hydrogen and halogen. That is hydrohalogenation. So that's addition reaction. So that's that.